Okay, so there we go. Great. So we're going to start today with policy gradient, right? And after that, we'll probably cover dynamic programming, some TD learning, SAC, Q learning, all the good stuff. And then we'll do some model-based RL and keep going. But we start with the simplest algorithm, which is policy gradient, and then we'll build to the like more and more complicated versions. Okay, so our structure for today is going to be, we'll start by deriving what the policy gradient is, right? How many of you are familiar with it already? Some small number? Okay. So we're going to start by deriving the policy gradient. For those of you already know it, go to something else. We'll come back to the more interesting bits by the end of the class, right? But then we'll talk about what's the challenge with policy gradient. Why doesn't everyone use policy gradient for everything? And then we'll talk a little bit about some of the modern tools, so like natural policy gradients, going to TRPO, going to PPO, going to GRPO. We almost certainly won't hit this by the end of the class, but we'll cover it. Okay, so let's recap a little bit. And our problem statement in reinforcement learning, not in imitation learning, is that we have an agent, which is represented by a policy pi theta. It's going to be a neural net that takes in state, outputs the distribution of our actions. Our goal is to learn the parameters of this policy. Okay? And we want to do it, unlike imitation learning, so that you maximize the expected sum of rewards, right? So I'm always a little sloppy with discount, but like generally you'll have like a discounted sum of rewards. So you might have something which is like gamma to the t, right? So our goal is going to be to try, and we don't have access to any expert demonstrations so far. We'll come back to the case where we have some expert demonstrations and offline to online RL and all that by the end of the class. But for now, we're going to say we have nothing but access to the environment. We have to figure out these parameters for phi theta just through interaction so that you maximize the expected sum of rewards. Okay? That's the setting we're going to assume. We're going to generally operate in the infinite horizon setting, right? So we're going to have a stationary policy, not a time index policy, but it doesn't matter too much. Our goal is going to be to maximize these rewards under the following assumptions. The first is that your rewards are additive, right? So we want to compute the sum of rewards, not the product of rewards. There's other formulations you can think of with rewards, but we're going to assume the rewards are additive. And we're going to assume that the dynamics can be sampled, but you don't have the functional form. And the rewards appear magically, like they come from the world, right? And so a lot of the research, both in LLMs and in robotics, is where the rewards come from. How do you learn them? How do you use them? Blah, blah, blah. But for now, we're just going to say they appear, right? And we're going to try and learn from them as they appear. Okay. That's the setting we have, right? We have sampling access. We'll get S, A, S prime, R sequences. Yeah? And we're also going to assume that we're like reset to some initial state distribution. All of these expectations are computed under some initial state distribution. Start with all of them in initial state distribution. Be the same. So we're gonna stick to this, but there's like extensions of a lot of the ideas from RL into like optimal control. Like the Bellman equation is like the AGB equation, and planning is kind of model-based RL is like the same thing. So, okay, so in this setting, we want to maximize the expected sum of rewards. How should we do it? Like we have this objective. Our goal is to maximize the expected sum of rewards. And the tools we have are, optimization, supervised learning, blah, blah. Like how should we do it? Like what's our guess before I tell you the answer? How should we maximize the sum of rewards? Like forget about RL for a second. Just like if I had to maximize the sum of rewards, how would you do it? Gradient descent. Great. Yeah. So we're going to do gradient descent. Are there other ways that you would maximize reward?
If you're given we said that the state transition was unknown.
Sample from it, but it's unknown. But
You can learn.
you can learn it, right? So the third option we're going to do is to learn it, right? So we can say learn p hat
And then you could do like search.
and then do search. Great. That's model-based RL, right? And what else can you do? Right? Either
just like sample.
just sample, and then but you can sample and then you need to like get into the parameters though, right? And so as in you want to find the parameters that give you the best. So are you saying sample parameters?
Like, yeah, let's double step and then see what kind of configurations we need.
Right. So one thing you could do is you could just do like filtered BC, which is like sample a bunch of stuff, filter out the good stuff, and then do supervised learning. Oh, it's kind of what we're going to do. But the three types of approaches we're going to cover are gradient descent, dynamic programming, and then model-based optimization, model-based stuff, right? And so the easiest one is gradient descent. Each of them have their own pros and cons. Like gradient descent is great because it'll like usually converge the best solution, but it's like slow and it takes a ton of samples. So you don't want to put it on robots. Dynamic programming is great because it's efficient, and you don't have to predict like that. Super duper efficient, and it transfers across problems, but you have to like predict pixels or you have to like build a model of the world, which might be harder than just acting the world. So we'll cover the pros and cons once we cover the methods, but generally, this is kind of the spectrum of things that people think about, plus minus some. Okay, cool. We're gonna start with gradient descent, right? Yeah.
Yeah, I wanted to ask, how is it possible to calculate gradient descent because this function like looks many steps into the future, but we don't know what that will be until we actually like sample them.
So we are going to compute a gradient with samples.
I see.
So we're going to compute like an estimate of that gradient with samples.
Okay.
Good question. Cool. All right. So if we start with gradient descent, gradient descent, most of us know what it is, but generally if you have a function, you want to just follow the direction of the gradient to reach the global or reach the local optimum, right? So a function like this, I want to take small steps with the local gradient and take like many steps till I get to the optimum and stay at the optimum, right? And so you compute the gradient at every single step iteratively and take a small step, compute the gradient again, take a small step and repeat, right? And so generally the gradient descent objective looks something like this. You say theta I plus 1 is theta I plus some step size alpha times the gradient of your objective, let's call it J, with respect to theta, with theta set equal to theta I, right? And so usually for convergence, you have to like make certain assumptions about the structure and like the step size, right? But in this case, we're not gonna say anything about the global convergence of policy gradient. We're just going to talk about the local convergence. Right? There's like some of you might do nice theory on this, but I think we're not going to talk about whether it converges or not. I can send out some papers on. Mariam Fazal here has, so you guys should look at this. Okay, we'll talk about this a little bit later, but you can think of gradient ascent as steepest ascent under the Euclidean norm, but it's not the only ascent algorithm you could have, right? But we're just going to start with gradient. Okay, so let's start with supervised learning. Right? Supervised learning is what we know and we love. And so we're going to take our imitation learning objective, just saying it's the argmax of S star, A star sampled from D or from your expert of log pi theta, A star given S star. And we're going to do gradient descent on this objective, right? And so when we apply gradient descent, we're going to say we're going to take the gradient and let's try and expand it because we're going to, I mean, we know how to do this, but we're going to see how it's different for RL, right? And so we're going to expand it. You can write this expectation as an integral. Let's remember that the expectation p of x f of x is always equal to the integral p of x f of x dx, right? And so in our case, we're going to take an expectation under some expert distribution, right? So this expectation can be expanded as the integral over s star a star of p of s star a star from the expert times log pi theta of a star given s star, ds star, dA star, right? This is like a double integral. Okay, so under some minor continuity assumptions, you can move the delta into the integral. But now the only term that depends on the integral is the log pi theta, right? And so what you're going to have is you will have an integral p of s star a star, the gradient log pi theta, a star given s star, ds star, dA star, right? Now, remind me of your name?
Martin.
Martin. As Martin was asking, we want to compute this gradient, but it's all these expectations and so on, right? So what we want to do is we want to take the gradient and convert it back into an expectation, right? And expectations are nice because you can compute them with samples, right? And so we have this thing. Is it an expectation? Yes, right? So it's an expectation. You can write this as the expectation of S star A star from D of grad log pi theta A star given S star, right? Just like invert the definition of expectation. And so the important part here is that we took the gradient of an expectation is the expectation of a gradient. And so essentially you can just think of this as like your teleport, because this term, let's delete all of this stuff, because this term here didn't depend on theta, you just like teleported the expectation inside. Sorry, teleported the gradient inside, right? And so you teleport the gradient inside the expectation. And so in supervised learning, you can always just think of supervised learning as you compute the gradient of independent things in your batch. You just average them and you take a step, right? It's easy. But we'll show how RL is not quite the same. Okay, does it make sense for how we got to the way you'd implement this in supervised learning is you take a batch. For each batch, you compute log pi, or each element of the batch, you compute log pi A star given S star. Take a gradient, it'll give you an individual gradient vector, then you average it, and that gives you the gradient you're going to take for supervised learning, right? Take a batch, compute individual gradients, average. Okay, so the important thing to convey here is one, when the probability distribution doesn't depend on theta, you can put the gradient in. And the second thing is you always want to compute your gradients in terms of expectations. You want to write your gradient as an expectation so I can compute it with samples. Because when I have this thing, right, I can use Monte Carlo approximation to say I'm going to draw n samples from 1 to n, compute log pi theta of AI given SI and average them, right? And so, or sorry, grad log pi. So the important thing is you want to move the gradient inside and you want an expectation. Cool. Any questions? Make sense? Supervised learning. Sweet. Okay, so now if we want to do this for reinforcement learning, I'm going to use a little bit of shorthand and then we'll try to expand it just because it'll make our notation a little cleaner. But let's say we have this expected reward objective. Let's write it as let's write in terms of trajectories for a second. So we're going to say that the expected reward objective can be written as expectation of trajectories drawn from p theta tau of r tau, right? So p theta tau is the likelihood of a trajectory being drawn when you have a policy. R tau is the reward of a trajectory, right? And so we're just going to say, I want to get the gradient of this thing with respect to theta, right? Cool. So the whole premise of policy gradient is just that this thing looks a little bit different than the supervised learning objective, right? So what's different about this objective than the supervised learning?
Theta is in the subscript.
Theta is in the subscript, right? So theta is in the probability, theta is in the distribution that generates the data, right? And so you have to be a little careful because you can't just like teleport the gradient inside it. And so you can't just simply compute the gradients of f. In this case, f doesn't even depend on theta, right? So you can't compute the gradients of f and average. You have to be careful because the thing that you're determining is the data generating distribution. Yeah. So if you compare them side by side, you can see the difference, right? This one has theta in the data generating distribution. This one has theta inside the expectation, right? And that's what makes it. So in this one, you teleport it in. That one, you can't teleport it, right? Okay. So that's what's going to be our pain point here. Like let's take this gradient, right? What we're going to have, the important thing is let's try to do some simplification. Okay, so we say gradient theta of integral p theta x f of x dx. Okay, we move the gradient inside again. Now you have an integral of gradient theta p theta x f of x dx. Okay. Now the problem with this expression is that it is no longer an expectation, right? There's no probability. It is only a gradient of a probability density function, right? And if it's not an expectation, then it's hard to compute. And so that's why it's like not so trivial to do policy gradient, right? Cool. Any questions so far? Supervised learning, RL, make sense? Cool. All right. So let's try to fix this problem. We're gonna try and take the gradient of this RL objective, and we're gonna try and deal with this. We're gonna try and convert the gradient into an expectation, right? So our purpose here is going to be to take the gradient of this objective and convert it into an expectation, right? So the gradient itself will be an expectation of something, right? And then we're going to make it such that you can implement it with autodiff, right? So you don't have to do any work. So let's start with our objective, right? We'll start with our objective. Remember, our objective was expectation p theta tau r tau. By the definition of an expectation, it's just going to be j theta, right? Now, we are going to compute the gradient of j theta with respect to theta. Okay, so if you want the gradient of j theta with respect to theta, we're going to compute the gradient. Remember, we can move the gradient inside the integral, right? And so we can write it as grad theta p theta tau r tau. Okay? And our issue now is that it is no longer an expectation, right? And so we're going to try and convert this into something that is expectationable, right? So how would we do that? Those of you who know policy gradient, don't speak up. The others, for the others. What's this trick? There's just one trick in policy gradient. How do I convert this into an expectation? So I have this thing that's not an expectation. Remember, the definition of an expectation is integral p theta x fx dx, right? So yeah. Because your reward is a scalar, right? And it's determined by the world. And so it's like hard to do that. But it's a good idea to like somehow introduce a probability distribution somewhere, right? So like, how do we get a probability distribution there? Any other thoughts? How do we get this to be an expectation? Yeah.
You multiply and divide by the probability.
That's right. So you multiply and divide by the probability, right? So the trick here is you just multiply and divide by p theta tau, right? Doesn't change anything. And then you just like think of this thing as f of x. Think of this thing as p theta x, right? And now it's an expectation again, right? And so the nice thing here is we didn't change anything. We just multiplied and divided and regrouped some terms, right? Question?
Yeah, but you still have theta inside the f, so how is it?
We already computed the gradient, right?
Oh.
So this is the gradient. So the reason this is a problem, right, is it's not a problem to just have a gradient inside the expectation. That's fine. The problem is that the gradient itself is not an expectation, so I can't compute it with samples. So as long as I have an expression that I can compute as an expectation, even if it has a gradient term inside, I'm okay, right? And so, yes, this term has a gradient and a theta and stuff inside, but that is the expression for the gradient with respect to theta. Okay, so we're going to simplify it some more to see the expression that you want to see. And what we want to do is we want to look at this particular thing, grad theta p theta tau divided by p theta tau, right? And we want to simplify it further. So is there a simpler expression for grad theta p theta tau? Can we use chain rule to simplify it? Yeah. That's right. That's right. Right. So you can, if you think of the chain rule, right? So the chain rule of probability says if you have the gradient of this thing with respect to theta, right? You can write this as 1 over p theta tau times the gradient of p theta tau with respect to theta, right? which is exactly this expression, which is, it is gradient of p theta tau with respect to theta divided by p theta tau, right? So this expression here, you can write it as grad theta log p theta tau, right? Okay, so we are going to do a little bit more simplification. And so just by using the chain rule, right, we can say chain rule for log, you can say that this expression now simplifies to p theta tau, grad theta log p theta tau, r tau, d tau, right? And this is nice because now I can rewrite this as an expectation, right? And so I can rewrite this as an expectation. I undo, like I just reverse the definition of expectation. So it's the gradient of the expected reward is the expected p of a trajectory multiplied by the reward taken with expectation with respect to. Oh, I cry myself to sleep, Jim. False. What the hell? I don't know where that came from. um, okay, so let's think of this as an expectation of grad log p theta tau times r tau with respect to the expectation variable is p theta tau, right? And so we'll try to unpack this intuitively, right? But what we did here was we took this objective, right, where we said we didn't know how to compute the gradient and we didn't have a tractable way of doing it, and we converted into and we showed that the gradient itself is an expectation of something we can compute with autodiff, right? So we haven't fully completed yet, but I will say that this thing is something you can compute with autodiff. You know the reward, you know how to sample from the trajectory, you know how to sample from the policy, so you know p theta tau. So this is something you can compute pretty, like you can compute computationally, right? You can compute in PyTorch. But so far I'm like kind of abstract. So I'm kind of abstract on like what is r tau, what is p theta tau? Like this is not something we can like implement in code yet, right? So let's take one more step. But generally this trick is what you'd call the reinforced trick. It's used all over the place. Like anytime you have anything like non-differentiable and you want to step over the non-differentiable thing, you just like do it this way. If you have like a non-differentiable R, you want to step over it, you can just like use the reinforced. Okay, so what we're going to try and do is take this thing that we've written in terms of trajectories, and then like try to express it in terms of state action tuples, right? So remember, the world is in terms of states, actions, next states, rewards, and we're going to try and express this thing in terms of states, actions, next states, rewards. Yeah. So remember MDP, we're going to start from some state S naught. We're going to take an action A naught. We're going to transition to S1. We're going to take another action A1. We're going to transition to S2 and so on, right? So it repeats. So when you look at the likelihood of any trajectory, right? So if a trajectory is written as S naught, A naught, S1, A1, S2, A2, etc., right? If you want to get the likelihood of a trajectory, you say it is the likelihood of an initial state multiplied by, so you can say the likelihood of a trajectory is P of S naught times P of taking the action A naught at S naught times the likelihood of transitioning to S1 given S naught and A naught, okay, times likelihood of taking A1 at S1 and so on, right? And so basically you can, this is, if you remember the trajectory view of sampling from our first lecture, you can think of like the likelihood of a trajectory as the likelihood of the first state times the likelihood of the first action conditional on the first state times the likelihood of the transition dynamics, right? And this is because the Markov property, you can like decompose it as the product of these individuals. So the shorthand version of writing this is like likelihood of the initial state times the product, the likelihood of the dynamics times the product of the policy, right? So remember, it's just like first step. So the same thing as the trajectory likelihood. So now we're just going to substitute this into our expression, right? And so the first thing we're going to do, remember our expression was expectation p theta tau, grad log p theta tau r tau, right? So we're just going to substitute this in for p theta tau. So log p theta tau is going to be log of product is sum of log, right? the sum of three different terms, log p s naught, plus sum log p st plus 1 given st at, which is basically log of the dynamics, right? And then you'll have a last term, which is log of the policy. Okay? So this thing, I just make sure to write this, dependent on theta. Okay. So remember, our previous expression was expectation p theta tau grad theta log p theta tau times r tau, right? Now, let's take the gradient of this thing with respect to theta. And so what happens? Gradient with respect to theta. Like, what is the gradient with respect to theta?
You get to eliminate.
Yeah, you got to eliminate these two terms. Yeah, you got to eliminate the two nasty terms, right? And you don't know the dynamics, you don't know the initial state distribution, but turns out you can't control them anyways, right? So they're you're just gonna set them to zero, right? And so the cool thing in policy gradient is that when you compute the gradient of log p theta tau, those two terms cancel. And so that's why it's called model free RL, because you don't need a model, right? And so you can write the gradient of log p theta tau as just the sum of the gradients of log pi at individual steps. And the way to think, like the intuitive way to think about it is like, no matter what theta you have, you don't control the dynamics. You don't control the dynamics function. You can control the actions and stuff like that, but you don't control the dynamics function, right? And so it doesn't affect. Good. So what that allows us to do is to write grad theta log p theta tau as the sum of grad theta log pi theta at given st, right? And so remember, our policy is some neural net that takes an st and outputs some distribution p of at given st. You can like use torch dot distributions to take the log of that and then take the log of that, and then compute the gradient of that, right? So this thing is completely implementable in just autodiff. You don't have to do anything, right? Cool. Okay, so let's put the pieces back together, right? So the policy gradient, which is grad j theta, is the expectation. If you remember, it's the expectation of trajectories from p theta tau, grad log p theta tau times r tau, right? Now let's substitute the individual pieces. Remember, the trajectory can be denoted as a sequence of sampling. So you start by sampling the initial state, then the initial action, then the next state, then the next action, the next state, then the next action. So you just replace the expectation appropriately. Then remember, we just worked out that grad log p theta tau is a sum from t equal to 0 to t of grad theta log p theta at given st, right? And the reward is just sum from t equal to 0 or t prime equal to 0 to t r of st at, right? And so the important thing here is that like there's like brackets here. Right? So you kind of take this the sum of the grad log prob along the whole trajectory, and then you take the reward along the whole trajectory, and then you multiply those together, right? And so you're not just multiplying them one step at a time. Why is that? Why does that matter? No, it's not faster. Well, it could be faster, but that's not the reason. So you can think of one reason is that everything like it's a sequential decision making problem. So like you make a decision here, it also affects all the stuff in the future, right? And so it can't just be that you like say at time step t, I care about the reward at time step t. What I care about is the reward at every step in the future, right? And so it's important here to say that you're going to sum up grad log pi's along the whole trajectory. You're going to sum up rewards along the whole trajectory. You're going to multiply them, and then you're going to average them over all samples from your current policy. Okay? And then this expectation is nice because we know how to sample from that distribution by just like executing the policy in the world, right? And if we can execute the policy in the world, we can estimate it with Monte Carlo, right? Anytime I have an expectation and I know how to sample from the distribution, I just draw n samples and I average, right? And so what I'm going to do is I'm going to draw n samples. I'm going to draw n trajectories. For each of the trajectories, I'm going to compute this term, right, which is the sum of grad log pi's along the trajectory. I'm going to compute this term, which is the sum of rewards, right? And then I'm going to like average over each of those to get the gradient, right? But the important thing is that I have to draw trajectories from my current policy, first thing. Second thing is I have to sum up grad log pi's along a trajectory. I have to sum up rewards along a trajectory. I have to multiply them, and then I have to average them. Right? So you can kind of think of it as like I drew many trajectories. For each of the trajectories, I summed up grad log pi. For each of the trajectories, I also summed up r. I multiplied those together, and then I averaged them over all the trajectories, right? And so that gives us policy gradient. And so you're using a Monte Carlo approximation, and something you can just like implement. It's not that different than supervised learning, as we'll see, but it's like you can implement it. But the important thing is that you have to draw samples under your latest policy. You can't just draw samples from like another policy. Yeah.
Number of samples.
Many. It's a good question. It's often a hyperparameter, but the more samples you take, the better your approximation is, right? But in reinforcement learning or in policy gradient, often the challenge is variance. And so if you have this estimator, you'll see that it has like, we'll talk about a bunch of issues with variance. So when you have policy gradient, you typically will choose n to be really large, because if it's not, you'll have like gradients that jump around a little. Okay, cool. So let's try and intuit policy gradient, right? So the way I think about policy gradient is just like it's a glorified trial and error, right? So you're going to implement this kind of thing, but it's like essentially just glorified trial and error. So you can think of it as like, imagine I drew 3 different trajectories, r equal to 30, r equal to 100, r equal to -10, right? And what I'm going to do is draw those 3 trajectories, and then I'm going to like basically take all the actions in this second trajectory, and I'm just going to upweight all of them. Like, so I'm going to increase whenever I'm saying the gradient is grad log pi times reward, I'm going to like increase the likelihood of the states or the actions and states, or rather I'm going to increase the likelihood of actions at states weighted by their reward, right? And so I'm going to say that like, I'm going to increase the likelihood of each of those actions. So in supervised learning, I would just maximize the likelihood of everything, right? And here what I'm going to do is draw a bunch of samples and then maximize the likelihood of the good stuff more and the bad stuff less, right? And so just like, that's just trial and error, right? And so you're just saying sample, upweight some stuff, downweight some stuff, sample, repeat, right? But the important thing is you're drawing samples on policy, and you're doing grad log pi weighted by the future rewards, or like the past and future rewards. And so it takes into account not just your current reward, but what the outcomes are. Yeah.
In this information that there's only the reward signal at the end. We don't need the reward in the steps.
No. Why does it suggest that?
But you only take the sum of the.
You take the sum, right?
Yeah.
So like imagine if you got like, great reward in the middle. Like for instance, you like imagine you had a task where you like made the coffee and then you sat at the front, but the reward is from the coffee. Right? And so like that could have been in the middle of your trip. And you still want to take it.
Yeah, but what I mean is if you take the reward of the 2 times, you don't need to like have the reward at each step.
Yeah, so that's a good question. Basically, imagine if I had reward only at the end. That's often called sparse reward. And the challenge with sparse reward is that you like the likelihood of getting it. And so your estimator would be super high variance because the number of trajectories that actually get it is very low. And so it's nice to have like dense rewards, progress rewards, so you don't have to worry about like the whole horizon. You can even take like shorter steps. And so the point of like, often what people do in practice is they do reward shaping, which means that they like design these like more informative rewards. And those rewards basically reduce the variance of your estimate. So they're saying that like, I could get sparse rewards, but I might need like 10 million samples to find. But with dense rewards, I would have much shorter trajectory or much less trajectory. I'll still get a signal. Yeah.
What's the green line was that?
Like these ones? So,
Well, the distribution.
oh yeah. So this is like the distribution that you first sampled from, the red curve, and then you're saying that like you got rewards which were like low here and high here, and once you like take a step, your distribution shifts to increase the likelihood over here, decrease the likelihood.
Okay, so the green is just the updated.
The green is the updated, and the red is before. Yeah, good question. Okay, good. So policy gradient is just glorified trial and error, right? But that's going to come with some issues, which we'll talk about. But let's first just think through what the algorithm looks like, right? So what we worked out is that we can compute the gradient of the expected reward and you go through this loop, which is saying you collect some data, you sample a bunch of trajectories from your policy, that you execute them in the world. Then you compute your gradient as a Monte Carlo estimate. Right? The gradient is going to be like a theta dimensional thing. You're then going to take a step on your parameters. And then you can't take multiple steps because every time you want to compute your gradient, you need to recollect the samples. Right? And so the thing that makes this algorithm, which is called reinforced, expensive, is that you have to keep on computing. You have to keep on taking samples every time you want to compute the gradient. So whenever you do supervised learning, you just can keep taking the gradient on the same data, right? Whereas in reinforcement learning, because you control the data distribution, every time you take a step, you have to resample. Right? And so that's what makes this really hard. These are called on-policy algorithms. And so on-policy algorithms are just things that only use the latest batch of data. So if you look at this, update, you're going to use the latest batch of data and you're going to throw everything else away. It doesn't matter. Right? And so every time, the only place you use the latest batch of data is to compute this expectation. Right? And so the challenging part about this whole thing is that because I'm only using the latest batch of data, I have high variance, I have to like blow up my batch size, and I can't use any past data. And so that's what makes on-policy algorithms so expensive. Okay, so we'll have a whole few lectures about how to use past data, but if you're just looking at this algorithm, how would you think about using past data? Yeah.
Because I will use the samples from an earlier distribution, but rate them differently according to
That's right. So there's a nice idea called importance sampling. Right? So what importance sampling lets you do is that if you have an expectation according to some distribution Q, you want to compute this, but you only have access to some distribution P instead. You only have samples from some distribution P. Right? So what you can do is you can compute this expectation under Q as expectation under P of Q over P of X, right? And so there's the nice thing about we'll cover this in more detail, but like the intuition behind what Dean was getting at is like if I can reweight the data, then I can say even under if I want to compute the expectation under the latest data, I could still use the old data, but I just need to reweight them to account for the change in probability. And so we'll cover some of this in like PPO kind of does a little bit of this, etc. Yeah, more advanced topics. Right now, we're just going to take on policy. Everything's on policy. Okay, so let's compare this to supervised learning. So reinforcement learning, we saw we have grad log pi, we have sum of reward. We have supervised learning, which is also grad log pi, right? Or grad log p. So they're similar in some sense, but what's different about them? Like if I look at the grads and the logs and the p's and I do some pattern matching, they look kind of similar. So what makes them different? Yeah,
There's no like sequential.
that's right. There's no sequential element to the supervised learning. And you're not collecting data from your latest. So you're like, that thing is just the gradient estimator for one step. You have to keep on iteratively collecting data under your latest policy. So like this thing is a little bit misleading because like this expectation also depends on theta, right? Whereas this thing does not. So it's related, but not quite the same. But the nice thing is that you can use a lot of the same machinery. Cool. So the way I think about policy gradient is that you just sample a bunch, you select the good data, and you increase the likelihood of the good data, decrease the likelihood of the bad data. That's it. Okay, so how do we implement this? Let's think about how we implement this in something like PyTorch or JAX. All we're going to do is let's see, I have a more concrete example. Let's think about supervised learning. You'd implement supervised learning as something like this, right? So you say you're going to compute some logits. You're going to take in your state. You're going to compute some logits. You're then going to compute the cross entropy loss with your actions, right? And then you're going to try and minimize the cross entropy loss or maximize the likelihood. And so that's how you'd implement supervised learning. And if you're trying to implement RL, it doesn't look that different. So you're still going to compute the logits, right? So let's say you had a categorical distribution, you're still going to compute the logits. You're still going to compute the cross entropy loss. In this case, the cross entropy loss is kind of the log likelihood. But you're not just going to minimize the cross entropy loss, you're going to multiply the cross entropy loss with the rewards, or the sum of rewards, which in this case we're calling our Q values. And then you're going to like take the average of that and then minimize that loss. Right? So the main difference between supervised learning, this is like the thing you've seen all the time, is that you just do cross entropy loss and take the mean and minimize it. Here we're going to do cross entropy loss, multiply it by your rewards, then take the mean and then minimize it. Right? And so the difference here is like this step here. You weight your negative log likelihoods or by your Q values. And Q values are your sum of rewards. And so you'll implement this in your homework, but that's basically the difference.
And what would be sample?
This is this like the sampling is like external to this. So this is once you've collected a set of samples.
Okay, and then Q values come from.
The Q values are just like sums of the samples. In this case, what we're going to do is we'll call this like Monte Carlo sum. So you'll just like sum up the rewards along a trajectory. So you would have sampled a set, you would have sampled a batch of, trajectories. Your Q values are essentially just the sum from that step onwards, right?
And so to add like the extra data from previous run. And to the Q values.
But then you have to like reweight them. Yeah, exactly. Cool. So our Q values are just our sum of rewards, and we're just going to multiply across. Like remember that in a discrete setup, your cross entropy loss is your log loss, right? Or in a Gaussian, it will be the log of a Gaussian, right? But you're going to take your log likelihood, you're going to multiply it by your rewards. And that's going to be what you call your surrogate objective, thing that you like take the expectation of and minimize. Cool. Often what you'll do in your homework, and often in most robotic settings is you'll use a Gaussian. Like that's the most common parameterization. So for a Gaussian, you're going to parameterize phi of A given S through something like this, right? So you can think of like S going into a neural net kind of like S goes in, you have like some neural net, and outcomes do things, right? The first is your mean. So let's say your action was like A-dimensional, right? Typically your output is 2 times A-dimensional. The first half is your mean, and then the second half is typically your log standard deviation. Okay. So why is it your log? Why do we do the log standard deviation rather than the standard deviation? So for what's it? It's unbounded range, right? Yeah, it's unbounded range. And whereas like your standard deviation has to be positive. And so it's like, it allows you to like output something that's like unbounded range. And so what you typically do is you'd output like log standard deviation and then you'd exponentiate in your log likelihood. Right? And so your likelihood will look something like this. Remember that you can see that this likelihood itself is a function of theta through the mean and the covariance, right? And so for most implementations in a Gaussian, you're not going to deal with the full covariance matrix, although you could. You often will deal with like a diagonal covariance. You could also consider like some, Cholesky decomposition. But like typically you'll have a diagonal covariance and you'll have a mean. And so you'll output like something that is like 2 times A-dimensional. Right? Another like trick that lots of people use is that they like actually make the standard deviation parameter not dependent on state. So they just say that, we won't have this thing depend on state. It is just like a separate parameter, which is the same across all the states. And that just like makes optimization easier sometimes. Not all the time though. So cool. So you are just gonna like apply just like use torch dot distributions, compute log likelihood, multiply by rewards, maximize. That's it. Cool. The challenge here though is that policy gradient by construction needs you to be able to auto diff through log likelihoods. And so when can this be hard? Well, if you have something like a diffusion policy or a diffusion model, right? You don't have analytical likelihoods or they're hard to compute. In those cases, it's hard to take grad log probs. If I don't have log probs analytically, it's hard to take grad log probs. And so the reason there's a whole field around fine-tuning diffusion policies and diffusion models is because it's hard to compute grad log probs. Okay. So does it work? Kind of works. Here's some examples of, a variant of policy gradient, which is PPO, which lots of you have heard of, which is not that different than policy gradient, actually working in practice. And yeah, I think many of the most popular RL algorithms are policy gradients, but this version of the algorithm doesn't work. And you'll try to implement in your homework and you'll see that it's pretty bad, but it will get better over time. Okay. Any questions? Yeah.
Slides. Yeah, so for here, when you talk about a Gaussian.
Yeah.
Is that a distribution over possible outcomes, or is that a distribution over probability of the given action?
No, it's a distribution over it's a distribution over possible actions. So it is a probability that you take an action A. So it's not a distribution over distributions. Yeah.
So this works for continuous settings. Is there an analogous?
For discrete, you just output like a table. Like you will just have like your neural net take an S and output like a set of logits, which is like A-dimensional. Let's say you had n discrete choices, right?
Does this run into the same mode collapse problem from
Yeah.
the imitation?
So imitation learning doesn't have mode collapse, it has mode covering typically,
Oh,
right?
yeah.
So you like mode averaging. Now reinforcement learning doesn't have the same problem because this objective, right? In this objective, you are controlling the data distribution, right? So it's like in mode covering, what happens is you don't control the data distribution. And so you you can't like miss any modes because you can't control the data. Whereas in reinforcement learning, you control the data. So it's kind of closer to reverse scale. So you will be mode seeking. So cool. Okay, we're at 12 or 1:50. Let's take 2 minutes, 3 minutes, and we'll come back.
Go for it.
Yeah, so I think it's like so, no, I will be fine. Like my noise around. I was looking up, but that's what you do. No, I mean, my actions be HS. Yeah.
I post all the recordings and this in. So you're welcome.
Oh, yeah, we ran like 4 miles and gas starts. Yeah, people were
Separate out the logs.
I guess you can always choose to do. Okay. It's just the choice of like probably works.
Like why does it work in some problems?
Yeah, like some problems you might find that like there's like like some parts you're like and I think it's just how precise to be in the right. Whereas some problems like you have more solid around or you have five knowledge. So I think it depends on how
what layer was
how
50 layers and
how you narrow it.
So it's like really
For reinforced, is it generally uniform? Like is the precision that you need generally uniform?
But it's like this is literally the
Okay, yeah.
So it's like
some of it shows that there's
like that is a complex problem.
Okay, so you would like
zero
maybe just by both.
500 column layer or 500,000. It's like relatively small. It's just like so I expected that I get this okay because there's only one kind of dimension of it, so there's even like no dimensions into But if I did this with say like 20 dimensions and then like oh, like you can
Yeah, so for the reward, I don't know if you know about six, is it easy to gather your reward at each step?
It's very hard.
Right.
Yeah,
We're kind of not talking about that stuff for now, so.
We're not talking about it for now. So like in LLMs, it's often referred to as the process. And so like, first steps, right? And in robotics, you often call it regeneration. But a lot of the research is how do you provide that rewards. And simulation, it's often easier to provide. But even then for simulation, imagine you're a humanoid, right? Like how do you provide steps like in every mode?
Yeah.
So I would say it's like an open question, how to provide dense rewards or how to learn in the case of cars.
What do you mean like learn?
Like if I've really delayed far away rewards, the problem is I left it. So then you'll see a learning curve.
Okay, yeah, that makes sense.
I didn't notice that like training was
Okay, let's keep going. So policy gradient, as we described it, nobody uses policy gradient. Williams invented this in 92 or something. Nobody uses it. But let's try to understand why is it hard, right? So the way I like to think about it is like a little pictorially, right? And so if you look at this objective, right, what's happening is that you get what is called a single sample estimate, right? So basically for every single grad log pi that you have, like imagine that you had, a particular state action pair, right? You only get a single sample estimate of how good it was, right? It's not like I took many different samples here. And so like if I got super lucky or if I got super unlucky, like things get really high variance, right? And so what's happening is that for every single state action tuple, you're getting a weighting only by like your like the way I like to think of it is you're like wiggling a rope, right? Like your trajectory is like a rope, you're like wiggling your rope. And for every choice, like every point on the rope, it is like beholden to all of the decisions that you made in the future, right? And so what's happening then is it's hard to tell which things were good and which things were bad because you've like tied together the fate of each decision along that rope, right? And so you in policy gradient, you like take the state actions pairs, you increase their likelihood only according to the rewards in the current trajectory, right? And so remember this is not function approximated, this is nothing. This is just like literally the sum of rewards in your current trajectory. So if I got super unlucky, super lucky, took a bad decision in the future, like even good actions will get low rewards, right? And so that's what makes policy gradient kind of hard, and that's why it's high variance, is that you're using the single sample estimate, which couples together all actions, right? So remember, we're like summing these up and then multiplying it by the sum here, right? And so you're saying that like the fate of like all the grad log pi's is dependent on the fate of all the R's. And so you're coupling together all the actions. You will find that it's like really susceptible to scale variations, especially across states. Like some states may have really high reward, some states may have really low reward. And so if you don't reward scale, it like tends to get super unstable. And if you have stochastic dynamics, you're susceptible to really lucky samples, right? Or even if you have a stochastic policy, you took like one bad sample, things that are good were rated bad, or you take one, you got lucky one time, things that are bad are rated good. And so that's what makes policy gradient challenging, but they're all kind of in the like realm of what you'd call variance, right? And so if you ever like, there's a bunch of nice papers analyzing policy gradient, and you'll see that like they compute the gradient and measure the variance. They compute the gradient many times, and they compute the variance, and it's like super duper high, right? Like you can think of it as it's like pointing you in different directions a lot. And to reduce that variance, you often will blow up your batch size, right? Like you'll make that n huge, like thousands to tens of thousands, right? Which on a robot is like tough going. Okay, so what we're looking for is to go from the single sample estimate, which is a high variance estimator, to something that looks more like this, right? So what you want to say, for instance, is that I took some decision to go from S to A, and then I like saw many possible features of how good that action was, and that tells me whether this action was good at this state or not, right? But why is this difficult to get? Like why can't I just do this? This seems great. Why can't I just do this? Why do we invent a whole field around it? Yeah?
You're doing another branching.
You're doing a branching, but that's okay, right? We're branching anyways.
Well, I guess there's another, like you, there's so many paths
Right.
to branching.
Okay, sure. Like it becomes exponentially large, a large tree. That's fair. You got it.
Maybe resetting through intermediate spaces.
Exactly, right. So the problem is that in most settings or in many settings, you can't just teleport wherever you want, right? Especially in like measure zero space, like a continuous state action space, you're like never going to revisit the same thing, right? And so like you never actually end up in exactly the same place. And so you're never able to tell multiple samples like that. Now, there's a bunch of like newer papers where they study like settings where you can reset. So for instance, in LLMs, you can reset, right? And so like there's a bunch of nice papers that reset to partial completions and sample many things from them. And that makes the variance a lot lower, right? And so like the keywords to look for like bind PPO or like bind sampling kind of does this kind of resetting and multiple. But in general, it's gonna be hard to do that, right? And so we're gonna try and reduce the variance of these three factors, right? Like coupling together actions, scale variations, and lucky samples. We're gonna try and reduce them one by one. Okay. So let's start by like thinking about coupling together actions, right? And so one important thing is that we're in a Markovian setting, right? So let's say I'm like along a trajectory, right? And so let's say I'm at some time step t. Now, right now what I'm doing is I'm summing up the grad log pi's along all the t's, and then I'm multiplying it by all the rewards at all the t's, including the past, right? But if I'm at some state, I'm taking some action, no matter what, if it's Markovian, no matter what action I take, it's not going to affect the past, even if it's not Markovian. Like you can't really affect the past. And so the important part here is that I don't actually like, let's say I was at some state t and I'm considering the grad log pi of at given st, it doesn't really make sense to multiply it with rewards in the past, right? And because you can't affect them. And so what we're going to do here is rather than multiplying it by the rewards along the whole trajectory, you're only going to multiply it by rewards in the future. Right? And so instead of multiplying it by return, you're going to multiply by return to go, which is like how many steps you have in the future. So this includes t prime, which is less than t. And so we're going to try and only consider t prime, which is greater than t, right? And so you can kind of think of it as like, I'm going to take the grad log pi here, multiplied by the whole thing. The grad log pi here, only multiplied by that. The grad log pi here, multiplied by that. And so you only care about the things that you affect in the future. And so what that serves to do is that by focusing only on the return to go, you're at least decoupling. You can't decouple from the future, but you're at least decoupling from the past, right? So if there was previous variance because of past decisions, you're at least removing that element of variance, right? So the simplest thing you can do is it requires a little more bookkeeping in your code, but simplest thing you can do is only compute return to go, not just return along trajectories. Cool. So that's the first idea, super simple. Only consider like be causal because you're in a Markovian setting. The second thing we're going to consider is scale variations, right? And so what do I mean by scale variations? So this is a slide I stole from Sergey, but if you consider like this figure, you have trajectories on the x-axis, and there's basically their likelihood is plotted through this curve, right? And their rewards are plotted through these lines, right? And you can see that I start by getting these three trajectories. Two of them have reward slightly above zero, and one of them has big negative reward, right? It's going to give me some gradient that moves this way. And then if I do something where I like kind of just push up all the rewards by a constant, right? In the case of infinite samples, it's unbiased, right? Because infinite samples will not affect constant will not affect the gradient, right? So imagine I had like an expected sum of rewards or R tau given p tau, like I add some constant to it, right? It's like doesn't affect the gradient, right? So it like doesn't matter in the infinite sample case. But in the finite sample case, you'll find that it has high variance. So like if you look at the previous example, like where it moved to, and this example where it moved to is like pretty different. And so it's a little hard to internalize this, but like I think one way to think about it is imagine that you had like two different states where the spread of actions was the same. So one of them was like +2, -2, and the other one was 502 and 498, right? So it's like the same spread of actions. And so like the weight of how much I should care about them should be the same, but one of them has reward of 500, right? And so I'm going to way overvalue that. Now, if I had infinite samples, right, like of course, like both of them would be normalized out. But in limited samples, what happens is like you kind of mix these two things, right? So you can think of the reward at any state action as the average difficulty of a state, right? Which is like this state gets reward 10 on or 500 on average, plus like the additional gains from the actions. I get 502 or 498. But if you just consider the standard policy gradient formulation, like some states may get +2, -2, some states may get 502, 498, and like you treat them very differently. And so even something that is like 498 will be way upweighted as compared to something that is +2, right? And so that leads to like instability and slow learning and like high variance in your gradient, right? So like the argument to be made is that the average difficulty of your state shouldn't affect your gradient, only the additional gain or loss from your action, right? So you only care about which actions are better than which other actions. You don't care that that state is 500 and that state is 0, because you care about like upweighting the decisions at those states, right? And so what we're going to try and do is we're going to modify the policy gradient by subtracting what we're going to call state-dependent baseline. In PPO, you often call it a value function, right? Or a critic. But in general, what we're going to do is we're going to say we're going to have a sum of rewards like we did earlier. We are just going to subtract some function B. We're going to call it a baseline. And the important thing is that it only depends on state, ST. Right? So imagine that you had a trajectory. You're going to consider grad log by here. You're going to consider the return to go. And you're going to subtract some B, which only depends on the current state. Yeah, and that's what you're going to call your state-dependent baseline. And the contention here is that your baseline is kind of like centering your returns, right? So it's going to bring that 500 to 498 thing and the +2, -2 things to the same scale, right? So it's going to put the same scale across all the states. Cool. But it's kind of like I just like added a random term, right? Like I just like changed the gradient. And we have to make sure that's sensible, right? So I added this B of ST, but I had this gradient that we like got from some fundamental first principles, and then I just added a term to it, right? Which is kind of random. So the question we need to ask is this like a reasonable thing to do? Right? So the question we're going to ask is if I look at this estimator and I subtracted a state-dependent baseline, does it increase bias, right? So we're going to empirically see, and you can show theoretically that it reduces variance, but does it increase bias? Is it a reasonable thing to do? Does it leave the estimator the unbiased, like the same, right? Okay, so the answer is obviously going to be that it's going to be unbiased, otherwise I wouldn't tell you about it. But let's try to work it out, right? Okay, so the thing we're going to try and prove in the next 13 minutes is we have this policy gradient objective, and we are going to try and subtract a state-dependent baseline, and we're going to show that the expectation remains unchanged. Yeah? Okay, so what we're going to try and do is we're going to start from the policy gradient. I'm going to write it slightly differently. Right? So if you remember how the policy gradient was, you sample, states, actions from that like long chain, and then you have like grad log pi, and then you like have a sum of rewards, right? And so I'm just going to write it in the stationary distribution form. So I'm going to say that if I sample states and actions from my stationary distribution, and I say basically the policy gradient is the expectation of S and A from my stationary distribution of grad log pi A given S times sum of rewards minus the baseline. Yeah, just the same policy gradient expression. And what I'm going to show is that like this expectation is the same as the standard policy gradient, right? So that B term doesn't, like we want that B term to not matter. It's going to reduce variance, but it's not going to matter in terms of bias. Okay, so how are we going to do it? Let's take this expression and let's separate it out into two terms, right? So the first term is the reward term, and the second term is the baseline term, right? So remember, this is your standard policy gradient, right? So this is policy gradient. I just want to show that this term is zero, right? So if I can show that second term is zero, which means in expectation, it is zero, right? Then I'll show that this thing's unbiased. Right? So if you go back to standard machine learning, we're just going to show your estimator's unbiased. That's it. Okay, so our quest is going to be to take this like second term and show that it's equal to zero. Yeah, everyone with me? Second term is only thing we're doing is we're separating out the reward term and the baseline term. Remember, the baseline is any state-dependent function, and we are just going to show that it integrates to zero. Cool. All right. So we're going to show this is zero. Let's see how we're going to do it, right? So any guesses at how we're going to show this thing is zero? Whenever you have a thing and you want to like get a zero in there, like what's the easiest way to get a zero?
Add something else.
We could add something and subtract. That's not what we're going to do here, but that's generally a good idea. We have a grad, we have a log. Like, how are we gonna, like, what's our trick? What are we gonna, like, it's useful to know the object we're working towards, right? So we want to get a zero in there somehow. So what things do we know are zero? So we know that log one is zero, right? And we know the gradient of a constant is zero. So in this case, we're just going to try and get it to the gradient of a constant. And so if we get it to the gradient of a constant, it's going to be zero, and then everything's unbiased, right? So we're just going to try and work this expression into the gradient of a constant. Cool. All right. So we have this expression. The first thing we're going to do is we're going to separate it out into the distribution over states, multiply that by the distribution over actions given states, right? So you have P of ST times pi theta of AT given S, right? Remember, you're taking samples under your current policy. So it's the state distribution under your current policy multiplied by the action distribution under your current policy multiplied by grad log pi times B, yeah? Now, let's invoke all of the stuff we learned earlier today, right? Now we have this beautiful thing, right? Like, what is it? What does it simplify to? Let's use the chain rule. What is the chain rule tell us? Yeah, you're gonna remove the log, right? So we're gonna get P of ST pi theta of AT given ST, and the gradient of log is 1 over pi theta times grad pi theta times B, right? So all we did is we used the chain rule on grad log, right? So 1 over pi times grad pi. Yeah. Cool. All right. So now the nice thing is pi and pi cancel, right? And so you have simplified this to P of ST times grad theta pi theta times B of ST dST dAT, right? Okay. So now we wanna get this to a zero. How do we do that? So we've simplified this to, sorry, it revealed too much. But let's say we have P of ST times grad theta pi theta AT given ST times B of ST dST dAT, right? Like, and remember, one integral is with respect to S, one with respect to A. Right? So like, how am I gonna get a zero in here? We have to just one more trip. So look at these integrals, right? Like, which things depend on S, which things depend on A, and which things don't. Right? So like, remember the baseline just depends on action, just depends on state, not on action. And the state distribution just depends on state, not on action, right? And so this term and this term you can take out, right? So you can say this is integral S, P of ST, B of ST, integral A, grad theta of pi theta, AT given ST, DAT, and like whatever, DST, right? So let's look at this inside term, right? It is basically the gradient. Now I can reveal. Oh. It is the gradient, is the integral of the gradient of pi theta, dAt ds, right? And so now, can I make that into a zero? Is it a zero? This guy. Yeah. That's right. You pull out the gradient, right? The same way we put in the gradient, you pull out the gradient, right? And so, say gradient comes out, right? So you get integral P of st, the gradient of integral pi theta at given st, dAt dst, right? And now you have the integral of pi theta. Pi theta is a probability distribution. So the integral is 1, right? And so now you have gradient 1, which is 0, right? So the trick is you just need to like pull out the terms that don't depend on A, and then you take out the gradient, and then you have an integral of probability, which is 1, then you have grad 1, which is 0, right? And so that gives you grad 1, which gives you 0. Amazing. Right. And so, but the important thing here is that your baseline cannot depend on action. And as soon as it depends on action, this thing cannot leave the inside integral, and then you can't get it to 1, right? And so baseline has to be independent of action. So there's a bunch of nice research on like state, what do you call it? Action dependent baselines, but they're like more complicated. Right? So typically in PPO and most other algorithms, you'll have like a value function that just depends on state. You can subtract it from your Monte Carlo returns. It'll reduce variance, but it will not bias your objective. Yeah. Cool. So it's unbiased. And so typically what most people will do in practice is that they'll learn, like, this thing doesn't tell us what the optimal B should be. It doesn't tell us what the optimal value function of the baseline should be. What is the thing that most reduces variance? It doesn't say, right? It just says that you like, no matter what B you introduce, it'll remain unbiased. But what most people do in practice is that they train what you'd call a critic in PPO or reinforce or a value function, right? And they just try to regress to the average rewards, right? And so they say that like for every state, you just regress to the average rewards. And if you regress to the average rewards, that gives you like the average difficulty of a state. So it kind of centers your returns. And so typically what you'll do is you'll have the policy gradient loss, but you also have a critic loss. And the critic loss is just trying to do regression to the average rewards. Yeah.
Then it's supposed to just, when you're sampling, take the kind of, so we have 498 and 502. It's just kind of average that, says 500, subtracted.
Because you don't necessarily have multiple samples from, you need functional approximation because you don't have multiple samples from the same state. Right, from exactly the same state. So what this will
Because
do,
you can't teleport.
yeah, because you can't teleport,
Then you would
do that. Exactly. So if you could teleport, you do a lot of things. And so basically what you do is you say like, I won't necessarily have like things like this. What I will instead have is something like this, something like this, something like this, something like this. And then I kind of regress to the sum of rewards, right? Okay, so the value function is typically just the average rewards, right? If you solve it with L2 regression, and then you just subtract it from your policy gradient, and you just do like the plain policy gradient. The reason I think like in general, like critics are super overloaded words. Like what is a critic is like overloaded, but in policy gradient, the critic is the V function. And it's okay if your V function is a little wrong because it just is still unbiased, right? So the cost of fucking up your V function in policy gradient is much lower than if you mess up your Q function in like TD learning, right? So in general, like policy gradient, you can get away with worse critics, and in TD learning, you like struggle with worse critics. Okay, I think we are basically at 2:20. This is going to take me like 10 minutes next time, but yeah, we'll see you guys on Monday. Thanks. you want to work this out at home, it's basically trying to figure out what is the optimal baseline. So if you want to figure it out at home, that is.
Yeah.